for the NASA ISRO, which will provide unique data on Earth's ecosystem, ice, and natural hazards. He has authored numerous influential papers and received multiple awards for his outstanding contributions to Earth science from space. Sir, we are honored to have you here. I welcome Dr. Paul Anderson to the stage.
Thank you. Just in case, I think it's okay. All right, so good morning again. The title of this session in your agenda was slightly different. It said NISAR and its applications, but it looked to me like it would be a good thing to go over SAR fundamentals with this group, because in order to really understand the power of the NISAR data set and exploit it using machine learning techniques, I think you need to have a reasonable understanding of what it means, what the radar data actually means. So how many of you actually have studied synthetic aperture radar before? Okay, so maybe most of you have, in which case maybe you don't need to hear about the fundamentals. But many of you have not. It's always good to get a refresher. I was originally intending to speak for 90 minutes this morning, but I've been asked to try to condense my slides to 45 minutes, and that's going to be difficult. So probably what's going to happen is at 45 minutes, we will see where I am, and tomorrow I have another lecture. We will continue that tomorrow. And at the end of the 45 minutes, if you tell me, this is too simple, we know all this already, tomorrow I can change the lecture to be something different. Okay, so without further ado, I probably already used 5 minutes of my 45 minutes. I'm going to start. So just so you know, I think many of you have seen this before, but could we turn the lights down in front by any chance? Lights. NISAR is a joint collaboration between NASA and ISRO. It's a huge satellite, 12-meter diameter reflector, 9-meter boom, and a very large structure down here, having 2 synthetic aperture radar instruments on it. It was a marvelous partnership. All of this hardware is contributing enormous amounts of data that we're going to hear about tomorrow and later in this class. And understanding the characteristics to really exploit it are important. As I said, it has 2 radars, one at L-band, 24 centimeter wavelength, another one at S-band at 9 centimeter wavelength, roughly. NASA built the L-band instrument, ISRO built the S-band instrument, and they were integrated together over the last 10 years to make the system that is now collecting so much data. The system has a very wide swath, 240 kilometers, that allows us to get complete coverage of the Earth every 12 days from both the ascending and the descending part of the orbit, and some other characteristics that you'll learn about throughout this meeting. But I just wanted to say that these characteristics of this mission were specifically designed by the science community working with the engineers to be able to get dense temporal and spatial sampling, to get comprehensive global measurements, and targeting new science and observations with a free and open data policy. How many of you have already looked at some NISAR data? Same people who raised your hand about knowing about SAR already, so that's great. This is just the beginning. Okay, this is acknowledgements. I've worked with many colleagues over the years. This slide package was actually put together for another seminar that I gave many years ago, actually. I updated it for this class a little bit, specifically for an IEEE workshop like this. These are some of the great names in the field over the years who have developed materials at the station. So here's the outline. I probably won't get all the way, I will not get to SAR applications today. and I may not make it all the way to the end of SAR phenomenology. We'll see. So the radar concept, for those of you who know nothing about SAR, is very straightforward. You have a transmitter, and often the receiver is located in the same electronics box as the transmitter. A pulse of energy is transmitted from the radar and interacts after propagating some distance at the speed of light with some object that you're interested in. It bounces back, some of the energy bounces back and is received by the receiver. That's the radar concept, pretty straightforward. Very much like sound waves where you make a noise, it propagates, it bounces off some material, and comes back to your ears. So the transmitter is the mouth, ear is the receiver, and the signal itself has characteristics when you transmit it. In this case, you say hello. It comes back altered in some fashion and with lower amplitude. So we use the properties of comparing the transmitted waveform, which in this case is hello, to what we receive, and try to infer the characteristics of the object that we're looking at, in this case, the canyon wall. With radar, we're using electromagnetic energy, and in general, we can control with the radar how we generate that energy. So we can pick a specific frequency, a range of frequencies, transmit that. We can control its orientation of the electromagnetic field. It can be vertical or horizontal, or it can be some combination thereof. And when we pick the frequency and radiate in a particular direction, if we go a far distance from the source, you can think of that as a wave that's propagating as a planar wavefront. That's described somewhat cut off at the bottom here through an electromagnetic field that has an amplitude, and it has a phase, where the phase is a combination of the time dependence variability, frequency times time, down here, and the spatial variability. So these waves have the as well as the phase of the received echo. So one characteristic of radar is that we are measuring the net return of the signal coming back from the surface. So if we transmit the signal from an antenna, that wave propagates down. I said it propagates as a plane wave, but if you're close enough, it's really kind of a spherical wave. The signal propagates down in some radiated antenna pattern of the antenna that we're using. And the signal from equal distances will come back to the radar at the same time. So if you look down like this, and you have a very wide beam, you will receive an echo from this point here, as well as this point here, at the same time. So looking straight down, you can't really distinguish what side of the aircraft you're looking at, this particular dimension. And in 3 dimensions, you would have an ellipse like that. So generally for SAR imaging, where you want to have a unique relationship between the range that you're measuring and the position on the ground, we want to avoid this situation. So what do? You all probably know, we make an antenna beam that's quite a bit narrower than this, and then we tilt the whole beam to the side so that there's a unique relationship between range and position on the ground. We typically operate these radars in microwave frequency ranges. There's the spectrum that you're all familiar with. Microwaves are in the centimeter to meter to millimeter range. And these are the typical operating frequencies of radars. NISAR is operating at L band, which is 24 centimeters, and at S band, which is, in our case, 9.4 centimeters. But there are many, many other radars I'm sure you're aware of. The RISAT mission from ISRO is at C-band. Many X-band satellites commercially available now. So because these wavelengths are so different from what we see in the optical domain, we are looking at very different phenomenology when we look at radar images. And that's a good thing. So I think I already said this. This is just illustrating the principle of the radar coming down, back, signal going down and coming back, and we measuring the travel time. We also measure the energy that is received at the receiver to understand the properties of the pixels on the ground. Okay, so how do we achieve resolution in the range direction? If we are interested in specific point targets on the ground, we want to resolve those. Say we are interested in the distribution of cars in a parking lot, so we want to resolve each of the cars individually. Then we need to have a signal that we transmit that will allow us to make that determination. So if we have two cars next to each other like this, we'll call them point targets. We want our transmitted signal to be narrow enough in the ideal case so that the signal echo that comes back from each of the targets is distinct. They don't blend. So in this case, you can see that the echo width scattering off of this point target coming back will be unique and distinct from the second point target. So that's a good thing. Typically, though, we cannot transmit from space a very narrow pulse that would allow us to make these kinds of distinctions and be able to build the radar effectively. The power levels would be too high to be able to transmit a very narrow pulse. So we need to do something else to try to build up range resolution. And we do that by doing pulse compression. So if we have a long pulse, which would be longer than the resolution we would like, but we put a waveform on top of it that has frequency diversity, as you can see here, we call them chirps, typically in the civilian SAR sector. Then the signal that propagates down to the ground will have characteristic frequency behavior interacting with one point target. The other one will have the same characteristic frequency behavior, but the frequencies will be displaced in time, and therefore they can be compressed to be able to build up resolution. So even though these targets, the envelope of these targets are overlapping, by exploiting the frequency diversity using a matched filtering technique, we can create a much narrower pulse. We use frequency content to build resolution. So that's for the range direction. Now let's think about a radar on a moving platform. So we have an antenna that's on our spacecraft or our aircraft. It's transmitting a beam of energy that illuminates a large area on the ground. The range direction is this direction going across the swath, and the azimuth direction, or a long track dimension, is going along the track. So we just said that if we transmit a pulse in the range direction, if we use a coded waveform, then we can build fine resolution in this dimension. But in the other dimension, we have this very wide footprint. If we have a wavelength of 24 centimeters, an antenna that's roughly 12 meters in length, then the footprint size of that radar on the ground is going to be 20 kilometers or so. So that gives us a very wide footprint and very low resolution, which is not what we want if we want to build up high resolution images. So we need to do something to try to take care of that. These are just equations describing the beam width of the antenna and at the ranges of interest, what the footprint size would be. So we get in our received energy, we get all the energy that's being illuminated in this area here of the pulse coming back and being integrated into one number as we fly along. That's not what we want. So we already talked about the match filter. If we're looking at a point target on the ground, like a car, and we image it with this chirp, we get a receive signal that looks like this function that we transmitted. After we do the match filtering, we get something that is much narrower, like a sync function. We do this for every pulse that we transmit and we're flying along the trajectory here. And as the ground surface changes in its characteristics, the received echo as a function of time or as a function of range will have a different shape over the swath duration elevation. So we use these variabilities in the received echo to try to reconstruct better resolution in the other dimension. So if you were to look at a very idealized image of raw acquired data from a radar, where we're flying along this direction and the range direction is going across, and we had a point target that is located right here, then that chirp signal that we're transmitting has this quadratic phase or linear frequency characteristic. But as you move away in time from where this position is, the distance is slightly different. It's different. The distance from here to here is different from the distance from here to here. So you get a different phase value that's associated with each of those chirps. So you can see there's also another chirp in this other dimension. So we get a chirp in this dimension, and we get a chirp in this dimension. We should be able to exploit that for getting high resolution imagery. So after doing the range compression of the point target in the range direction, we now see that we have this background. This is the compressed chirp. We have a very narrow chirp here, but in the other dimension, we still see the full set of energy across the azimuth direction. But you can see clearly in the phase here, the color is phase, that you have a quadratic variability of phase in that dimension as well. And that then gives you an idea that you could do the same kind of processing in azimuth as you do in range to get a better resolution. This is just defining some terms. We talk about the elevation, the look angle here, theta L. We talk about the range to the target. We talk about the incidence angle, which is the angle from the look direction to the local vertical. If the Earth were flat, which it isn't, you would have theta C equaling theta L. But because of the curvature of the Earth, these numbers differ by 3 to 4 degrees depending on where you are on the surface. The swath is defined as the distance from where the beam footprint illuminates the ground from near range to far range. So those are those terms that we'll be referring to as we go along. So when we transmit a signal of a particular frequency and we're flying in a particular direction, as we change the perspective of where we're looking in the radar footprint, we will get a Doppler shift, which is the velocity vector dotted into the look direction that will change in sign and in magnitude throughout the beam. So that gives us then frequency content from a single transmitted frequency that allows us then to have resolution. The more resolution we have, the more frequency we have, frequency extent we have, the more resolution we have. So for SAR imaging, we're flying along, as you can see here, and at some point we encounter a point target. It's before we get to the broadside direction, so you have a blue shifted signal coming in here, and as you fly away from that target, it becomes red shifted. So over the time that this point of the ground is illuminated, you get frequency diversity in the observation over that period of time. So using that frequency diversity, you can just imagine taking a Fourier transform. That's like a synthetic aperture synthesized long antenna, many kilometers in length, that allows you to build up resolution also in the azimuth dimension. So remember I showed you that quadratic phase in the azimuth dimension. That comes from the fact that the range, as a function of position along track, is changing with the position along track in this fashion. And if you simplify it, it becomes essentially a quadratic form here. So the range, which is related to the phase, is quadratic to first order. And if you look then at the phase, which is multiplied 4 pi over lambda times that range, then you get this expression for the phase, quadratic in time. The derivative of that is the frequency, linear in time. So we get linear frequency variability, and that's the Doppler frequency. So if you look at the Doppler frequency as a function of time, you can see that it's changing linearly, and while the phase changes quadratically. So this is why we call these kinds of images, standard images, range Doppler images, because we're measuring in range and we're also illuminating a footprint that has Doppler diversity at any given point in time. Sometimes antennas point forward, sometimes they point backwards. The shape of this curve, the quadratic phase curve, or the Doppler curve is the same, it's just the spectrum that this image will be shifted forward or back in the frequency domain. Another way of looking at the synthetic aperture is as though we have flying along, we image a wide area, our point on the ground is imaged over many points as we fly along. And those antenna points then can be considered as the synthetic aperture because of two-way propagation. It's basically twice the illumination distance. And by essentially assuming that these things are all observations on a particular aperture, correcting the phase for that range distance, and then summing them all up will give you the high resolution. So here is our raw signal again. That's after range compression, and then using the same kind of compression technique in azimuth, you can see that point target is now reconstructed to be a point target, the constant phase in the middle, and then some side lobes which are due to the finite extent of the signal. And Dr. Kumar will give you a much more sophisticated interpretation of this stuff than this later. So I think I'll skip that. So that's the basic introduction to SAR. Probably all of you knew that, but maybe a couple of you didn't. The first synthetic aperture radar flown in space that any of us could look at data from was called CSAT. That was launched in 1978, and it lasted around 3 months in orbit before the power system on the spacecraft failed. But in those 3 months, it was able to create a set of data observations that were essentially transformative for science researchers. They saw things in the radar data that had not been seen before, really. Over, for example, oceans, they could see wakes of things that were under water, such as submarines. Over land, they could see surface features that were fundamentally different in their phenomenology from optical imagery. And they experimented with techniques that I'll be talking about here for interferometry that allowed us to see millimeter scale deformation of the Earth. So a very exciting mission. Unfortunately, it only lasted 3 months. And now, 40 years later or so, we have NISAR, which was something we've been working on for 40 years to get into space. So what can radar tell us? It can tell us many things about the Earth. We have the ability to control the amplitude of the transmitted signal. We can control the polarization, as I mentioned, the orientation of the electromagnetic wave that we send. We control the time and the phase very precisely, and we can choose our wavelength accordingly as to what we're interested in. So if the distant object will scatter the signal back towards the receiver, and it alters the amplitude and polarization of the phase, just like that echo example I gave you, and it will do it differently for different wavelengths. We can take that information and try to invert it for what is happening on the ground. So as I said, we see fundamentally different things with SAR than we do with optical imagery. Here's an excellent example of that from an image that was taken in 1981 by the SIR-A mission, the Shuttle Imaging Radar, that followed CSAT. And this is an optical image in orange of a sand sheet in Sudan. And overlaid on that is a radar image from the survey system showing fundamentally different signatures than what you see in the optical image. That's because the radar wavelength is 24 centimeters, and it's relatively insensitive to small particles, such as sand. It's the sand sheet. The radar signal penetrates through the sand with some attenuation, of course, scatters along the rocky surfaces below the sand, which could be many meters deep, propagates back out after it scatters, and then comes back to the radar. So what you're seeing here is the signature of the buried ancient river channels that exist in this sand sheet. So it's very good for paleo studies and also good for archaeology by being able to see below the surfaces. So micron scale wavelengths of optical, see the surface. Centimeter scale wavelengths, radar see below these kinds of surfaces when they're dry and small particles. So we have models for scattering in the electromagnetic field, and we can use some of the canonical aspects of scattering to try to understand the behaviors of what we see in a SAR image. So there's a theory called the mean theory of scattering, which is how an electromagnetic wave, plane wave, scatters from a sphere of different dielectric properties. And it turns out that the radar's cross-section of a sphere as a function of wavelength has different properties. For very small particles, the electromagnetic field looks like it's very, the wavelength looks very long compared to the particle size. They don't interact, and you get very little backscatter down here. For particles that approach the size of the wavelength, so 24 centimeters for L-band, you start to get these resonant interactions between the sphere and the wavelength itself. So you get quite a bit of cross-section, and that backscatter cross-section is roughly the area of the cross-sectional area of the sphere. So that's very important. Small particles, not much scattering. Large particles, more scattering. So by picking your wavelengths appropriately, you can be sensitive to different particle sizes. If you didn't want to penetrate through the sand, you would pick a very short wavelength that's around the size of the sand grains. You can also look at classical scattering from one medium to the next with a planar surface. You get particular behaviors of the Fresnel reflection coefficients, and those are a function of the incidence angle of the wave, depending on how that goes. So you can use those properties to understand the characteristics. You can combine these techniques to try to understand scattering properties as well, defining surface roughness. So for a tilted surface, you might have a facet that operates a little bit like an antenna, and it radiates off of this dimension with most of the energy going in that direction for a flat surface, but some of it may be being scattered back towards the radar. Smooth surface will scatter like this. You won't see anything in the backscatter dimension, but if the surface is rough, you'll get more energy going backwards. So you can create surfaces, artificial surfaces, that are a combination of facets and small rough inclusions, or even particle sizes. And these things can be used in models to essentially determine whether the backscatter you're getting from a signature makes sense or not. There's a characteristic called the Rayleigh roughness that says how high a surface needs to be, or variability of a surface needs to be, in order to declare that it's rough. And you can imagine that it's going to be wavelength scale dependent. And this is the Rayleigh roughness criterion. If the height is less than basically an eighth of the wavelength, then it's considered smooth. If it's higher than that, then it would be considered rough. And that would mean you get a considerable amount of backscatter coming back to the radar. So you can just look at an image, and if it's dark, because the radar signal went down to the ground and bounced away, then you know it's a smooth surface. If it's bright, then you know that it's a rough surface at the scale of a wavelength. So generally, you can look at the backscatter, which we often use the symbol sigma, to have a characteristic like this as a function of the look angle. So when you're very close to looking straight down, you're mostly seeing the surface as though it's a facet. So if you're looking at the floor, it looks very flat. As you move away an angle, you start to get other effects. You lose energy because much of it goes off in the other direction. And then towards higher angles, you start to get a coherent effect called Bragg scattering, where you are matching the radar backscatter to the wavelength of the radar and the characteristic scale sizes of the surface. So instead of just going down continuously with angle, you get this sort of resonant effects at the far angles. So armed with those very heuristic approaches, you can look at a radar image and try to understand its characteristics. So it's complicated, as many of you probably know if you looked at radar data. We're looking off at an angle. The reason that I stated earlier, we want to have unambiguous relationship between range and position on the ground as best as possible. But if you have topography, these constant range locations will have different projections onto the topography. And that means that you'll get more facet scattering, so more brightness of the surface as you tilt the surface towards the radar. That only makes more sense. This area is bigger than this area projected from that dimension. So you get a brightening effect on the front side of topography, and you get a darkening effect on the back side of topography. Every now and then you'll get a situation where everything, all the slopes are in one range style. That's called the layover condition, and you don't have a unique mapping of range to position on the ground. And then there will also be cases where it's completely shadowed, where the slopes are too great and you see nothing. So all of these effects create a backscatter brightness variability that you need to interpret as a remote sensor. And it could be due to the topographic effect, it could be due to smoothness versus roughness. You see here, you can have agricultural areas with corn rows that would have variable brightness, Bragg scattering effects. In mountains and in urban areas, you get layover and shadow. Forests tend to be quite uniform. We'll talk about that why in a minute. And urban areas often have these layover effects too. So your job as a remote sensor is to understand each of these signals, understand the topographic variability, understand the brightness and what that means in terms of the characteristics of the surface. We do this through the radar equation, which is just a long way of describing what happens to the signal as we go from the radar itself, transmitter, down to the surface of that. We transmit a certain amount of power. The antenna we choose has a certain characteristic gain that redirects the energy that you're transmitting into a narrow beam. So that gain is a multiplier. It propagates the distance r, so the power density decreases as the range increases. The power density at the signal at the target will be reduced by this factor. Then we scatter from the area itself. We propagate back and lose even more power. And then we receive that power density in a particular area. There are system losses, and then this is the receiver noise. So this is all the signal power on receive, and this is the noise level received. So the signal to noise ratio is the ratio of that power to this noise power. So we measure this, measure the signal to noise ratio for any given pixel, and what we want to do is understand what that means for sigma. So we'll get sigma from this, we know all the other terms. And then once we have sigma, we can interpret that. But it's a little more complicated than that. That's because we have a coherent signal, and it has speckle characteristics. So if you take a laser pointer and shine it at a wall, you'll see a speckle pattern on the wall because the coherent laser signal is interacting with the micro roughness of the surface of the wall and giving you variable returns. The same thing happens with synthetic average radar images. So the signal comes down, it interacts coherently with all the scatterers that are on the surface. They could be different, individually different levels of backscatter amplitude and phase. And each one of them is a unique distance from a reference surface going back to the radar. So all of those values add up coherently to give you a net vector. Even if the backscatter, the average backscatter of the surface is the same as the next pixel over, you'll get a vector that looks like that in that case, and the next pixel over, which has a different arrangement of scatterers, you'll get a different net backscatter. So if you look at an image, a complex image, amplitude will have variability from pixel to pixel that is as variable as its intensity. And the phase of that pixel from one pixel to the next will be random. So here's an example of a radar image at full resolution. Doesn't come out so well here, but you can see that from one pixel to the next, it goes from very bright to very dark. That's just the amplitude, and that gives us a limit to what we can do in interpreting full resolution images. But we have techniques for removing speckle. The simplest one is just to average them all together, the pixels locally. So here's a average down image. You can see, probably not so well, but you can see that the variability is lower, and the features here are starting to sort of pop out. So we can get the average backscatter by looking the images down to coarser resolution. So that tells you that if you are designing a system, you probably want to get the finest resolution possible so that you can, when you do this averaging, you'll still have a good high resolution image. Okay, so wavelength matters. As I said before, the smaller the particle, the smaller the things you're interacting with, the less interaction you will get. So if you look at L-band signals, they tend to penetrate through the canopy. The canopy has small scatters, leaves that are a few centimeters long, L-bands many more centimeters than that. So you can see through the canopy, it scatters from larger structures. At C-band, 6 centimeters, you tend to be somewhere up here in the canopy. S-band is somewhere in between here. And at X-band, you tend to see mostly at the tops of the canopy. Similarly, for dry soils, you might expect L-band to penetrate more deeply than the other frequencies. And for ice, you can see considerable penetration into ice surfaces. I don't know how this looks to you from where you're sitting. This is L-band, this is X-band. You can see quite clearly that the X-band, to me anyway, looks much more uniformly bright. That's because everything looks rough to an X-band radar, right? Everything is at 3 centimeters, everything looks kind of rough, except for maybe water, which is here. That's very dark because there was no wind on that particular day. Whereas here at L-band, you can see a much greater differentiation between some areas and other areas, which are less bright, or less rough, I should say. So polarization we talked about, and we'll just say a few more words about it. We can define the polarization of the electric field to be whatever we want to transmit. NISAR has the ability to transmit horizontally, vertically, or in a circular sense, where you put a 90 degrees phase shift between the two and transmit simultaneously on each beam. This is true for both the L-band and the S-band system. And so, in general, we might have elliptical polarization. But the beauty of polarization signal is that you can think of the surface that you're scattering off of as a polarization filter of a kind, where it's basically selecting certain polarizations for coming back to the radar. And from measuring the polarization on receive, you can then differentiate different surface types. So here's an example, very high level example of from the CRSS system. The different colors here, combination of frequency and polarization, but the dominant feature here is that the streets in some areas are oriented parallel to the radar flight direction, perpendicular to the range direction, whereas other places they're not. So you can see very clearly from the polarimetric signature these orientation differences. Just an example of how polarization really can distinguish different structures from others, at least long wavelengths. So we measure what we call the scattering matrix, which is basically the relationship between the incident field in H and V polarization, horizontal and vertical, to the scattering field. And that's through this matrix here. And that matrix is related to the scattering cross-section. So if we measure the scattering cross-section, we can determine these values, and from this value, these values is an entire field of polarimetry, radar polarimetry, designed to understand what is actually happening in the surface, on the surface, either at its volume scattering, double band scattering from buildings, and the like. And I think you'll hear a lot more about that later in this class. Here's just a quick example of just how powerful this technique can be. This is over some volcanoes in Africa from the CRSS instrument again. And you can see just from these polarimetric signatures, plus some wavelength diversity, just how distinguished the surfaces can be in terms of their roughness and orientation. Okay, I think I have 2 minutes. Where's this? So, 2 minutes? Up to 12:30. Okay, I can keep going, that's fine. Okay, so we've talked about backscatter per se, we've talked about polarimetry, now we're going to talk about how we can use the phase of the signal itself. I told you before that it's a coherent speckle generating system. So for these random scatters on the ground, you will get a random phase of this pixel relative to the next pixel. The propagation distance here is deterministic. And so from a single radar image with a random phase, we can't really say much about the phase. However, in interferometric techniques, we're looking at comparisons between two images. And if the surface characteristics here are the same in the two images we're comparing, then the differences will be related to the propagation distance. And that's what we use for radar interferometry. So the phase is related to the range, and we talked about before. So we're measuring the range to precision, differential range to very fine precision by looking at the phase. Okay, so I said before that the backscatter of any given pixel on the ground is related to the incremental scattering distances as well as the incremental scattering amplitudes of each of the elements within a scattering center. So it's a coherent sum of the individual things as well as individual distances. So that's what gives you this random phase. But if you image from a slightly different vantage point, where this angle is very small, then the differential distances will be very close to the same for those two, the first order. And that then allows you to form what's called an interferogram, which is a combination of these two signals. And that will give you a measure of the propagation distance. So this is just classic wave interference. You have two point sources here that are propagating to a surface. They will interact coherently or destructively or coherently, constructively, that's the word I'm looking for, as you go to different points along this observation surface. So you'll get these kind of interference fringes on a traditional interference pattern. That can be done for radar. So we have a standard image. This is of an area in California using the CIRC instrument again. The radar image is backscattered. Those topography effects I talked about earlier, you can see very clearly. Brightness on the slopes that are tilted towards the radar, darkness on the slopes tilted away from the radar. So you know there's topography there, but you don't necessarily know what it is. But by measuring from two different vantage points, we get these two interfering wave patterns cutting through a surface here. And so by looking at the phase coherently of the difference, you see that same image on the previous page now as an interferogram. These phase values are representative of the topography in this region. So this is a great way of measuring topography if you have two images acquired from slightly different vantage points at the same time. So we did this back in the year 2000. Many of you have any of you heard of the SRTM mission, Shuttle Radar Topography Mission? Okay, you've heard of it, good. You actually have used the data for the last 20 years. Maybe didn't even know that you were using it. It was in Google Maps for a long time. Now everything's been replaced by Copernicus DEM, but this was sort of the first uniform global topographic digital map. And we created those two slightly different vantage points by putting a 60-meter deployable boom on the shuttle and an outboard antenna here that served as the second antenna for our interferometry. And from that, we could create really fine resolution topography of the Earth. This one is supposed to show you that we discovered an impact crater that may be the actual KT boundary extinction event that people theorize just by looking at the topography. If you look at the imagery, it's hard to see. So lots of great things to be done for topography. But what NISAR is designed to do is not topography, it's designed to do surface deformation. And in this case, we are still doing interferometry, but we're hoping not to observe from a different vantage point. We want to observe from exactly the same vantage point. So for the first pass, we get a measure of the distance in the phase to a distance. But we can't use that because of the speckle noise that's introduced on the ground. However, if we come back again and observe from exactly the same vantage point, and if maybe you didn't notice, but the ground is now moved, it's subsided. We have this extra path length here. If the surface remained with the pixel, with the scatterers all in the same place, but it just moved, then we can actually, in the difference, form an interferogram that shows the displacement. So here's the first pass, we make an image. Here's the second pass, we produce an interferogram. And in this case, we're imaging an earthquake that happened in California. In this case, we're imaging the subsidence of an oil field where oil was extracted from the ground and the surface subsided. So we're looking at fraction of a wavelength scale variability of the surface. The wavelength is 24 centimeters. The noise is low in the image. We can measure millimeters worth of displacement using this differential technique. All right, just a few words on correlation. The signals that we have are not perfect. They have noise associated with them. There's various sources of noise. One of the sources of noise is just the fact that our signal to noise ratio is not always high. If the signal goes down and it hits a flat surface and bounces away, with very little energy coming back to us, the signal level will be low and our phase noise will be high. So that would be a bad thing. And then if the geometry is changing from one observation to the next, that can also introduce these speckle-related decorrelation terms. Decorrelation relates to the phase standard deviation. Phase standard deviation relates to height accuracy or the displacement accuracy. So correlation is something that is good to know, important to know, and can actually be used as a signal for understanding how the Earth is changing. Correlation definition is straightforward. You have one signal, multiply by its conjugate, and take the ensemble average of that, normalize it by the powers. If the signals are deterministic, the correlation is 1. If the signals are non-deterministic, then in this averaging, you get less than 1 correlation. And sorry about the color here, but the variance of the phase was related to correlation in most cases by this formula. So the higher the correlation, and the more the number of looks, the lower the phase variance will be. And it's the averaging you do. So if you have an image and you average pixels together, you can also beat down the variance of the phase. So the phase noise, as I said, contributes to height or displacement errors in interferometry. And we would like it to be as low as possible, or at least what it is for our modeling purposes. Just as an example of how we calculate the correlation, I'll just do it for the thermal noise case. Here we model the signal as having our X scatter, the propagation phase, and a noise curve. And the second signal has the same characteristics but an independent noise term. So if you go through the equations of calculating a correlation using these expectation operators, you can get something that looks basically like SNR. Oops. I deleted one of the slides that was before. Basically, you get 1 over 1 plus the noise over signal ratio, or SNR over 1 plus SNR. Turns out when you multiply these together. So the higher the SNR, the better the correlation. The lower the SNR, the worse the correlation. And another aspect is in terms of baseline correlation. If the vantage point of these two observations is far enough apart, then these speckle patterns start to look less and less similar. So the longer the baseline, the more decorrelation you get. Unfortunately, you can't see the equation here, but basically the correlation due to the baseline is a function of the baseline. And it's also a function of the resolution. And if we had more time, we could go into it in more detail. But that's an important factor. One reason why the baseline for NISAR is designed to be close to zero. We repeat our orbit to within 100 meters everywhere all along the orbit, which is very hard to do and also fantastic at power estimate. It basically means there's zero baseline correlation for NISAR. Okay, so this is my last slide today, and this is just summarizing what it is we're trying to do. We are measuring interferograms. We look at the phase. The phase tells us how much the ground has moved, or topography, if we're measuring topography. We can look at the correlation. Correlation tells us how much the ground has been disrupted. And we can look at the polarimetry, and that tells us what the surface types are on the Earth and what they mean for example, biomass or biomass change, wetland inundation, all the things that we'll be talking about later in this workshop. So I think there's like a few minutes left for questions, but tomorrow I'll focus specifically on NISAR, tell you more about the mission itself, the characteristics of the data, and many of the applications that we have been doing and hope to do with NISAR. Thank you for your attention. Yeah, if you have any questions, you need to use a microphone. Okay. Looks like there's one in the very back. Thank you for paying attention in the back.
Sir, I have used QGIS software to take random images. I'm not able to get different images. All images are being same. Any specific reason?
What do you mean they're all the same?
While taking images, they will come differently. No, sir. They are not coming in the particular software. Maybe mistake in the software or any specific reason that they will come different.
So are you talking about NISAR data in particular?
SAR data.
Any SAR data. Okay, so I think, I don't know anything about other SAR data, but I know if you're using QGIS with NISAR data, which is in a specific format called HDF5, you need, at the moment, you need to do a few little tricks to get it to be read properly. And one is you can take the file name and change it from .h5 at the end to .nc. And in theory, I've been told, QGIS can read that. If you want to spend the money on ArcGIS, already it reads it. You don't need to do anything. So if that's what you mean by different, I think that's the trick for getting NISAR data to work. Yeah. Okay, so you all knew everything already, so thank you for your attention. Now it's time for lunch.